So for this morning, we continue with our discussion on matrix. Yeah? So the last time that I mentioned to you is about parity. So this is a discrete symmetry. Because rather you would say that it is what you call mirror symmetry. And the eigenvalues are plus or minus 1. Because you get reflect and then you get reflected back. So the eigenvalues are only has a value of 1. So previously in the last lecture I already mentioned to you that the operation of this parity operator, which previously we call U, U to represent a general operator for symmetry operators, which are basically unitary. So this one, we know that if it act on this wave function in the spherical coordinate, then you know that suppose theta is the what do you call it, the eigenvalue for this operator, then you know that the operation of this theta itself is equal to pi minus theta, and pi is pi plus pi. So these two here is just a repeat after making one whole turn. So basically this and this is the same. But then when we factorize into the radial part and the angular part, then we know that this angular part is the spherical Bessel function. Okay, so this is what we call the spherical Bessel function. And then of course the spherical Bessel function has this special property that when the parity acts on it, it gives you minus 1 to the power of L. And back to the original wave function. Okay. So this is how you get this theta times minus 1 to the power of L as the eigenvalue of P. In this coordinate, in the spherical coordinate, okay? And so what is eta? Eta itself is plus or minus 1, which is the mirror symmetry. Okay? Whereas to the power of when it is multiplied with minus 1 to the power of L, it is the total eigenvalue for the whole wave function. So this one basically is for the what you call intrinsic parity. Okay. Whereas this whole eigenvalue of P is the total parity. So we try to distinguish between eta, which is the intrinsic parity, with the total, which is times the minus 1 to the power of L. Now, suppose you have two particles, and you can generalize to n particles. So I'm just giving 2. So you have, say, let us have 2 particles under the same potential. this could be a pair of nucleon, or a proton and or a proton and a neutron, or two protons. See, this is an example of, say, a halo nuclei, where this is the main nucleus containing, I don't know how many proton and neutron, but say this is a proton, this is a neutron that is far from the nucleus. It has its own orbit here like this, and this one has its own orbit, and this is the core nucleus. So this is an example. So then each of these, we say that the intrinsic parity. So here the eigenvalue for P, for this system of P, for this system is just suppose this is the value P, parity. It will be eta 1, eta 2. So this is equal to particle 1, equal to particle 2. So this is the intrinsic parity of each of the particle, whether it is proton or neutron, and minus 1 to the power of L, where this big L is L1 plus L2. You know, this P, the central, I mean the compact nucleus here is actually the VR. Okay. So this L1 as L2 is the angular momentum of proton with respect to the central nucleus, and L2. So this second particle, sorry, P1 or L1. So the angular momentum of each contribute to the total. Okay. So this is how you, and because this value of plus and minus 1 is arbitrary, so the intrinsic parity of particles are arbitrary, then you have to have what you call convention for intrinsic parity. And this is important, especially if the particle has its antiparticle. So basically the convention is that, number one, quark and charged lepton, the eta is plus 1, and anti-quark and anti-lepton have eta of minus 1. So that is kind of convention that people take. And why this? Later we will see that the direct equation follow this symmetry, or rather obey this convention. And you know, in beta decay, later we will see that it doesn't conserve parity. And because beta decay involve W particle, the gauge boson for weak interaction, and involve neutrino, you will see that in weak interaction. Example, decay involve W plus minus. which doesn't or violate parity, eta is undefined. For this neutrino and antineutrino, so they are undefined. So this violate that. Now let's go to the other symmetry. I mean, I can go on to give you some other example of discrete symmetry. Later we will see that, and it goes on to even to string theory, where the name changed to duality, which is called T duality, S duality, and so on. More complicated, but it is actually a kind of symmetry. Okay? So we don't want to go into that. Let's go now to gauge symmetry, which is continuous, but it can be made NUOU continuous. Yeah, it can also be discrete.